In this video, we're once more again looking at partial fraction decomposition. Now for this particular example, you'll notice that now that we have an x minus 3 squared in the denominator. This again throws some wrenches into some problems. The idea behind this is that we have some repeated factors, is what we call them. Since they're repeated factors, there's potential for the denominator to have had a different starting position. So what we want to handle then is this time is I'm going to have a over x, again linear factor in the denominator, constant on top. That's obviously that first factor. Plus, I'm going to go ahead and do an x minus 3 in the denominator, because it's still possible for us to have, when we added these fractions together, an x minus 3. Now what has to happen, however, is that for us to have had 3 or less fractions when added together, that had to have an x and it had to have this squared term. So I'm going to go ahead and write that squared term in the problem. This is what we call the repeated factor. So if I had a power of 7 here, then it would have to be x minus 3 is 1, x minus 3 squared is another, x minus 3 to the third, then to the fourth, then to the fifth, then to the sixth, then to the seventh. We have to have every possible power of that factor in the denominator of their own individual fractions. Now this factor right here still counts as a linear. Even though it's squared, this is going to be x minus 3. That's the factor. It happens to be repeated one more time than normal. So this is really the setup for this. And the reason, again, the real heavy reason behind this is the fact that these two things could have been all by themselves added together. But there is a possibility with the numerical values on top of this fraction that this middle term could have been there to start. So we have to account for that. And in doing so, we do come to what should be an appropriate conclusion. So now, with this problem, we're going to go ahead and do the exact same things that we did in the previous examples. X minus 18 is equal to a, and I'm multiplying both sides by this entire common denominator. So the x's are going to cancel out, leaving me with x minus 3 quantity squared, plus my b is going to be left over here with the x minus 3. One of those factors is going to cancel out, leaving me with x and an x minus 3. And then finally, the x minus 3 squared is going to cancel out, leaving me with plus c times x. And again, I'm going to simply follow through the exact same rules of the method in which I abbreviate the problem and avoid your matrix solutions. So in this case, I'm going to let x equal to a number. Let's let x equal to, I don't know, 0 for the first case. That seems nice and smooth. If I let x equal 0, this term and this term go to 0, I'm going to have a negative 18 equals to a times a negative 3 squared. Again, assuming all my x's in here are replaced with 0, this is what I'm going to have left, which means that a is going to be multiplied by a 9, which is going to be equal to negative 18, and therefore a is equal to a negative 2. That provides me with the value of a. The next step I'm going to do is I'm going to try and pick x equals to another value that seems to make things nice. So in this case, 3. If I pick x equals 3, you'll notice this term and this term go to 0, and this term is left over. So this time I'm going to have 3 minus 18 is equal to 3 times c. 3 minus 18 is going to be a negative 15 equals to 3c, and therefore c is equal to a negative 5. Hey, that was real smooth, picking those two numbers very particularly. Again, it's not magic, it's not random, it's very specific. I'm picking a number such that this factor goes to 0, and that makes this factor also go to 0. And then I'm going to pick a number such that this factor goes to 0, and that makes this factor go to 0. Now, we have a problem. There's no more specialized factors for me to pick. This is going to happen every single time you're looking at repeated factors. If I look at a repeated factor such that I have a power of 2 or a power of 3 or a power of 4, I'm going to have to do some little magical finagling work. But this is actually identical to the way that I finished out the last problem in the video, such that, or the last problem in the last video, such that I'm going to pick x equals to a nice number. I'm going to hold off on picking that nice number just yet while I look at the problem and I go, what's going to make this thing relatively nice? Well, I could pick x equals 1. Because then this x would be 1, this x would be 1. These things might be a little bit problematic. I think what I'm going to do is I'm going to pick x equals 4. There's a reason for that, and I'm going to go ahead and hold off on explaining it for just a second. I am letting x equal 4. Now, when I let x equal 4, that means that all my x's in this problem become 4. So I'm going to have 4 minus 18 equals a. Hey, I know what a is. A is supposed to be negative 2. So let me, in this problem, actually replace a with a negative 2, replacing still all my x's with 4 in this problem, so that's 4 and that's 4 minus 3, and then plus my c is now a negative 5, replacing that. Let me make sure I put parentheses around those just so I don't make any silly mistakes, and my x is a 4 again. So why did I pick 4? Well, I could have picked 1, but the reason why I don't want to pick 1 is because that would have made this thing right here a negative 2, and I don't really want to play with negative numbers if I can avoid it. So other than the numbers for a's and c's that happen to be negative, I'm picking numbers such that everything else becomes positive to some extent, and hopefully this will make my life a little bit easier. If not, that's no big deal. I can still go back and pick 1 if this seems to be too complicated for me. So 4 minus 18 is going to be a negative 14. This is equal to this 4 minus 3, and this is why I picked 4 in particular. I picked 4 in particular because I already picked 3 and I couldn't pick 3 again, but picking 4 makes this thing a 1. So now it's 1 squared. Oh, so this is just negative 2. And then I'm going to have plus my b times 4, and again, 4 minus 3 is 1. I picked that 4 intentionally that way, and then minus the 20 from this term over here. So now I'm going to go ahead and add the 2, giving me negative 12. I'm going to add the 20, getting me a positive 8, and positive 8 is supposed to be equal to 4b. In this case, my b is going to be equal to a value of 2. And you'll notice that this does allow me to find all 3 values by manipulating what I choose for x. When I finalize this problem, I should be plugging back the values for what the partial fraction decomposition is. So I should be ending up with something that looks similar to this. And you'll notice in this final solution written here that we did have to have both the x minus 3 and the x minus 3 squared case. So it is so vitally important that you do include the singular power and then every single power of that factor up until you have all factors of that powers included. So again, if this was, say, 4, then I should have this term, I should have x minus 3 cubed as a term, and x minus 3 to the 4th as a term. And that's going to finish up this particular example in terms of partial fraction decomposition. Let me go ahead and add one last piece to this video in regards to this particular problem. So 5x cubed minus 3x squared plus 7x minus 3, and this is divided by x squared plus 1 quantity squared. If I want to use partial fraction decomposition to manipulate this and tear it apart, notice that it's got a quadratic term now. And it's also important to note that if that was x squared minus 1, we could factor that, and therefore we'd have just a bunch of linear factors. But because it's not x squared minus 1, but it's x squared plus 1, the only way that the thing's going to factor is over the imaginary numbers. It can't be a factor over the imaginary numbers. So what we end up having here is what we call an irreducible quadratic. An irreducible quadratic is a quadratic such that it cannot be broken down any further. So now my denominator is going to be x squared plus 1 as the denominator in the bottom, and the same argument can be made for the second term because I have that repeated root. And let's reinforce that repeated root concept is that I'm supposed to have the secondary power of that. Now, what goes in the numerator of this problem? Well, the numerator, because this is an irreducible quadratic, the numerator will be a linear. And that means that the numerator of this one will also be a linear. So you'll notice in this case, because this is squared, that doesn't matter. It has to be there to finish out the problem, but that being squared doesn't affect what the top is. The top is only affected by what the denominator ends up being. So again, back in this problem right here, we did have a repeated root of x minus 3. And you'll also notice that when we set it up, it was a constant because the bottom was a linear, the top had to be a constant. When the bottom is an irreducible quadratic, the top has to be a linear. And again, for this one right here, you'd have to solve for A, B, C, and D and plug them appropriately back into the problem to solve for it. We will not be doing that in this video, but there could be examples in your homework that show this, that work through the problems in this concept. The rules for solving these don't change from the rules for solving any of these ones. It just adds an extra layer of manipulation into the problem is all.